to test a claim about a population proportion, we need to first review a couple of things about proportions and their sampling distributions. So the underlying proportion of the sampling distribution is a binomial distribution. So binomial distribution, remember, is got parameters n being the total number of trials, p being the probability of success in a single trial, and q being the probability of failure in a single trial, where p and q then are complements of each other. Now, there are lots of binomial distributions out there, but in this case, we need one that is going to be approximately normal, which actually is very simple to meet the conditions for. Those conditions are that the product n times p has to be greater than or equal to 5, and the product n times q has to be greater than or equal to 5. The idea here, of course, is that p is the probability of success, and therefore q the probability of failure. And if p and q are both relatively close to 50%, to 0.5, then it's very easy for the product n times p or n times q, and both of them actually, to be bigger than 5, with even a very small sample size. And the idea is that when p and q are both kind of close to 5, then we're looking at a distribution that is not skewed too much one way or the other. The bigger or smaller p gets, the more skewed to one side or the other this distribution would be. Now, it can still qualify as being approximately normal if the sample size is large enough to overcome the skew. So if we get p is only 0.2, which in turn would mean q is 0.8, then a large enough sample size to make sure that the product n times p is 5 would be enough to overcome that amount of skew. On the other hand, if we were skewed even further, if p was equal to 0.01, we would need a fairly significant sample size to overcome that very large amount of skew. So, for example, we would need a sample size of at least 500 times a p of 0.01 to qualify. So we would need a very large sample size to account for that level of skew. Now, the same thing happens going the other way. What if p was very, very, very large? Well, if p is very large, like 0.99, then in turn q would be very, very small. And that's why we have both requirements there. It's to account for being skewed in one direction or the other. Because as p gets very large, q gets very small. Or the other way around, if p gets very small, q is very large. So basically, by checking both, we're making sure that the smaller of the two is still a large enough product, meaning the sample size is large enough to overcome the amount of skew and still give us something that's approximately normal. Now, the reason these things are important is because sampling distributions for proportions follow the rule that if the underlying distribution is normal or approximately normal, then the sampling distribution will also be approximately normal. So the sampling distribution for p hat is approximately normal with parameters mu of p hat is equal to p. That is to say, the mean of the sampling distribution is the same as the probability of success in the binomial distribution. And the standard deviation of the sampling distribution is equal to the square root of the product PQ over N. Now, since we're looking at a distribution that is approximately normal, that means that we're going to use z-scores. So our test statistic will be a z-score, and the way we calculate a z-score, of course, is to take our sample statistic minus the mean of the distribution over the standard deviation of the distribution, which in this case would end up looking like p hat minus p. That's how much our sample statistic deviates from the center of the distribution in terms of the standard deviation. And this will be the test statistic that we use, whether we use a p-value or whether we use a rejection region test. That is our test statistic formula. So let's look at some examples. For this first example, a poll claims that 5% of adults in the United States believe they have seen a UFO. Suppose you decide to test this claim, and you ask a random sample of 250 adults in the United States whether they believe they have seen a UFO or not. 20 people respond that they have seen a UFO. So using this information, we're going to test the claim using the rejection region method at the 0.01 significance level. Okay, so we have several steps to take to prepare to do our hypothesis test. We need to identify, of course, the null hypothesis and the alternative hypothesis. And we also need to identify which of them is the claim. So remember, of course, the null hypothesis includes a statement of equality. So we're lucky enough to have the keyword claims right there in the first sentence. A poll claims that 5% of adults, not more than 5, not less than 5, that 5% of adults believe they have seen a UFO. That sounds like an equality. So they're claiming that the proportion is 0.05. Therefore, the alternative hypothesis would be that p is not 0.05. But the null hypothesis is actually the claim here. So it's always nice when the null hypothesis is the claim because the test is done on the null hypothesis. So it's nice when you're actually testing the claim directly. Now, we also need the significance level, which is, as always, given to us. Alpha is 0.01. And we need our test statistic. Our test statistic is based on our sample proportion. So we need that first, P hat is the probability in our sample that a randomly selected person has seen a UFO. And according to our sample, we had 20 people say they've seen one out of 250. This comes out to be 0.08. Now that is definitely higher than the 0.05 that was claimed, but that doesn't necessarily mean the claim was wrong. We have to see if it was significantly enough higher. So from here we go on and we find our test statistic. Our test statistic then is going to be the 0.08 that we found minus the 0.05 that was claimed over the square root of, well, the 0.05 is what was claimed, and therefore Q is 0.95 over the sample size of 250. Now please note, this entire fraction is underneath the radical. For the purposes of our calculation, we need to be very careful about that. So we could turn to our trusty calculator. And we get a test statistic here of 2.176. Now, before we go too far, I should point out there is one thing that we did forget to do here. before we just run off and start doing this, we do need to make sure that we have met the requirements here. And those requirements are n times p greater than or equal to 5, and n times q greater than or equal to 5. As long as those things are true, both true, then we can get away with doing this. So our sample size is 250, and the claimed probability of success is 0.05. And that comes out to be 12.5. And that is definitely greater than or equal to 5, so that checks out. Now, we don't actually have to check the other because, and we'll do it here just to illustrate the point, but we really only need to check the smaller one because 0.95 is significantly larger than 0.05. So 0.95 is going to give us something, a significantly larger total. So one of these will be smaller and the other will always be larger. So if the smaller one is bigger than 5, then the larger one obviously has to be bigger than 5. So we really can get away with just checking the 1, typically. We check whichever is smaller, P or Q, and that's enough to know that the other one is also going to be true. Okay, now, we are told this is a rejection region test. So we're doing the rejection region, and that means we have to find the critical value. So, the alpha is 0.01, and because the h sub a is p is not equal to 0.05, we're looking at a two-tail test. So we have to take the 0.01 and split it between the two tails, so that we have an area over here of 0.005 and an area over here of 0.005. Now, because this is symmetric, the critical values will be the same, but one positive and one negative. Now, that being said, our test statistic up here is positive 2.176. So we're going to want to compare this to the positive critical value. So this is where we again turn to our calculator, and to get the critical value, z sub alpha, we need to use the inverse norm command. And we need the total area to the left. So we've got 0.99 in the middle, plus another 0.005 in this left tail, means that our total area to the left is 0.995. And of course, we're using the standard normal distribution here. So our mean and standard deviation are 0 and 1 respectively. And what we get is a critical value of 2.576 if we round it off. That is enough for us to know that 2.176 is over here. That's where our test statistic is. So we are not in the rejection region. Our conclusion here is that we will fail to reject the null hypothesis. So our conclusion statement is that, well, let's take a look at our decision here. Our decision is that we fail to reject h sub 0. And h sub 0 was our claim. So our conclusion is that we do not have enough evidence to reject the claim. So yes, we did get, in our sample, we did get a proportion that was definitely not 0.05, it was 0.08. That being said, even though 0.08 was relatively large compared to our claimed value of 0.05, it was not so much larger as to suggest that the claim was wrong. So again, these are hypothesis tests. They are meant not to say whether the claim is correct or not, but to say whether our evidence is, whether our sample is strong enough evidence for or against the claim. Here, our evidence was not strong enough to suggest that the claim was incorrect. Let's look at one other example here. This one will use the p-value method. In this example, a research center claims that more than 55% of U.S. adults regularly watch their local television news. To test this claim, you conduct a survey of 425 adults in the U.S. and find that 255 respond that they regularly watch their local television news. We will use the data to perform a hypothesis test on the claim using the p-value method and a significance level of 0.05. So, as always, we will start with identifying the two hypotheses and identifying which of them is the claim. So, in this case, the claim is that more than 55% of U.S. adults. So, the claim is that the proportion is bigger than 0.55. And that makes it the alternative hypothesis because there is no statement of equality. The null hypothesis then would be the contradictory statement that p is less than or equal to 0.55. But the claim, in this case, is actually the alternative hypothesis. Now, we are also given the significance level, this time at 0.05. Now, before we go too far, we should just double check that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. In this case, q is the smaller value because p is 0.55. So our sample size is 425 and our p-value is 0.55. Our q value then is the complement of p, which would be 0.45. So again, we only have to check the smaller of the two. But in this case, 0.45 and 0.55 is very, very close to an even split of 0.5 each. So we're looking at a very slight amount of skew, very, very slight. So we shouldn't need too large of a sample size to make sure that we are approximately normal. And the sample size is 425. That should probably do it. And sure enough, we get 191.25. And that is definitely bigger than 5. Of course, then, if we multiply it by the larger 0.55, we're going to get an even larger value. And again, it's not really necessary to calculate both, it's really only necessary to calculate the smaller of the two, because, of course, the bigger of the two is going to be, naturally, bigger. So as long as the smaller of the two fits, the bigger one fits as well. But I'd say we're clearly very safe here. Now, from this, we are ready to go forward into the remaining part of our hypothesis test. For that, we need to know our sample statistic. So going back to the problem, we are told that we conducted a survey of 425 and found 255 responded that they regularly watch their local television news. So 255 out of 425. And that comes out to be a very nice 0.6. So that's good. From there, then, we can do our test statistic. Now, again, regardless of whether we're doing the p-value method or the rejection region, we need our test statistic. So our test statistic here is going to be, again, the p-hat from our sample minus the claimed p over the square root of pq over n. So we got 0.6. The claimed p is 0.55. And in the denominator, we have the square root of the fraction, 0.55 times 0.45, over the sample size, 425. And again, remember that entire fraction is underneath the square root. So, again, the trusty calculator. We get all that in there, and we come out with 2.072 if we round it to 3 decimal places. Now again, the difference between a rejection region test and a p-value test is that in the rejection region, we use alpha to define a critical value, to define this is the threshold of what is too far out and what is too close in. Or, what is close enough in. In the p-value method, we're simply going to take the test statistic, the 2.072, which would be about here, and we're going to find the probability of having a more extreme result. Now, I would like to point out, we know this is going to be a right tail test because of the symbol in our alternative hypothesis. It is a greater than symbol in the alternative hypothesis, and that tells us a right tail test. So what we need now is to find the probability that we might find a more extreme result than what we have. So our p-value is going to be from the normal CDF command with 2.072 as our left bound, 1E99 or some significantly large number as our right bound, and of course, because this is the standard normal distribution, a mean of 0 and a standard deviation of 1. So we turn to our calculator, and we get from this a p-value of 0.019. So that is the area to the right. The area of this shaded region here is 0.019. Now, we have to compare this to our alpha. If our p-value is smaller than alpha, which it is, our alpha value, remember, is 0.05. So if our p-value is smaller than alpha, the decision then is that we reject the null hypothesis. We're going to reject the null hypothesis. Visually speaking, the reason that we do this is because if our alpha is 0.05, that means it has a larger area than our test statistic did. If we look at this in terms of the rejection region, our blue test statistic is definitely further out than our alpha value, than our critical value. So because of that, we got a result that was fairly extreme. And it's extreme enough to decide to reject the null hypothesis. Now, what does that mean as far as our conclusion statement? A decision to reject H sub O means that if we're rejecting H sub O, we're accepting the alternative hypothesis. So what we would say here is that there is enough evidence to support the claim. There is enough evidence to support the claim that the probability is greater than 0.55. Which I suppose makes sense. I mean, the claim is that the proportion is greater than 0.55, and we found a proportion that was greater than 0.55, so that certainly seems to agree with the claim, right? The hypothesis test is enough to support that. It shows that, hey, we definitely got a pretty good sample because the probability of getting a more extreme sample is very, very low. So our example was maybe a little bit on the extreme side, but it definitely supported what the claim said. So again, just a couple of examples to look at both the rejection region method and the p-value method. But the basic idea, the procedure is pretty much the same. The new concepts here are, of course, the z-score, that we're using the normal distribution rather than the t-distribution, and that we need to check and make sure that the normal distribution even applies. So these are our new things. The z-test, the test statistic formula is a little different than it was for the claim about the mean. And we also have these requirements: n times p is greater than or equal to 5, and n times q is greater than or equal to 5. But aside from those two things, the rest of this is the same. We identify the null and alternative hypotheses and recognize which one is the claim. We need our level of significance. We need our sample statistic, which turns into our test statistic. And then we do either a rejection region or p-value method, depending on which we are instructed to use. And finally, write a conclusion statement based on the results of our hypothesis test and the nature of our null and alternative hypotheses and which one specifically was the claim.